Welcome to the Whispering Galaxy, where the universe unfolds its deepest secrets through gentle whispers of wonder. Tonight, we're drifting into one of the most peculiar corners of physics, where time itself seems to forget how to behave properly. I hope you found yourself somewhere comfortable, perhaps with a warm cup of tea and the lights dimmed low, because we're about to explore something that challenges everything we think we know about the flow of time. Before we begin this journey together, I'd love to know where you're listening from tonight. Are you tucked into bed in London as midnight approaches, or perhaps settling into an afternoon quiet moment in Sydney? There's something beautiful about knowing our little community is scattered across this spinning planet, all pondering the same mysterious universe. If these gentle explorations bring you peace, a soft tap of that like button helps more curious souls find their way here. And if you'd like to join us for more whispered tales of cosmic wonder, consider subscribing to keep these stories flowing. Now, I can only hope tonight's topic isn't so fascinating that it keeps you wide awake. But if it does, at least you'll drift off a little wiser about one of the strangest phenomena in all of physics. Tonight we're exploring time crystals and how they might hold the key to understanding something profound about the nature of time itself. Most of us think we understand time quite well. It flows forward, never backward, carrying us from one moment to the next, like a river that never changes course. We experience it as linear, predictable, and universal. But what if I told you that hidden in the quantum realm, there exist structures that seem to dance outside this familiar rhythm? What if time itself could crystallize into patterns that repeat not through space, but through the very fabric of temporal flow? Time crystals sound like something from science fiction, don't they? The name conjures images of glowing gems that manipulate the flow of moments, perhaps powering some impossible machine in a distant future. But the reality is far more subtle and, in its own way, far more extraordinary. These aren't crystals made of time in any literal sense, but rather quantum systems that exhibit a kind of temporal order that shouldn't exist according to everything we thought we knew about physics. To understand what makes time crystals so remarkable, we need to first consider what we mean by crystal in the traditional sense. When you think of a crystal, you might picture the clear quartz sitting on someone's windowsill, or the perfect geometric faces of a diamond catching light. What defines these structures isn't just their beauty, but their pattern. Inside a regular crystal, atoms arrange themselves in perfectly repeating patterns through space. This spatial periodicity gives crystals their characteristic shapes and many of their unique properties. For centuries, physicists understood crystals as objects that break spatial symmetry. While empty space looks the same in every direction, a crystal chooses preferred orientations, creating structure where there was once uniformity. The atoms lock into regular positions, forming the scaffolding upon which all crystalline materials are built. This breaking of symmetry is fundamental to how crystals form and why they behave as they do. But what would it mean for something to break temporal symmetry in the same way? What would a crystal look like if it repeated not through space, but through time? This question might seem purely academic, the kind of thought experiment that physicists enjoy, but which has little bearing on reality. Yet in recent years, this theoretical curiosity has become something much more concrete and surprising. The story begins with a Nobel Prize winner named Frank Wilczek, who in 2012 posed a deceptively simple question. If crystals can form by breaking spatial symmetry, creating repeating patterns in space, could there be analogous structures that break temporal symmetry, creating repeating patterns in time? He imagined quantum systems that would spontaneously develop a kind of temporal order, oscillating in regular patterns even in their lowest energy state. This idea was revolutionary because it challenged one of the fundamental assumptions about how matter behaves at low temperatures. According to classical physics, systems naturally settle into their ground state, their lowest possible energy configuration, where all motion ceases. It's like water finding the bottom of a hill, naturally flowing to the state of least energy. But Wilczek proposed something different. What if a quantum system could maintain perpetual motion even at its ground state, not by violating conservation of energy, but by finding a way to oscillate without ever winding down? The concept was so unusual that many physicists initially doubted whether such systems could exist at all. How could something keep moving when it had reached its lowest possible energy state? How could motion persist when there was no energy left to sustain it? The answers to these questions would require diving deep into the strange world of quantum mechanics, where the familiar rules of everyday experience often break down in surprising ways. At the quantum level, the notion of being perfectly still becomes problematic. Quantum mechanics tells us that particles can never be completely at rest due to the uncertainty principle. Even at absolute zero temperature, quantum systems retain what's called zero-point energy, a kind of irreducible jitteriness that prevents them from ever becoming perfectly motionless. This quantum restlessness provides the foundation upon which time crystals might be built. But zero-point motion alone isn't enough to create a time crystal. What's needed is a system that can organize this quantum motion into regular repeating patterns that persist indefinitely. The system must find a way to spontaneously break time translation symmetry, choosing to oscillate with a particular period even when no external force is driving it to do so. The first theoretical models of time crystals faced a significant challenge. Many physicists argued that such systems would violate fundamental principles of thermodynamics. How could a system maintain organized motion without eventually succumbing to disorder? How could it avoid the universal tendency toward equilibrium that governs all physical processes? These objections led to intense debate in the physics community about whether time crystals were truly possible or merely a theoretical mirage. The breakthrough came when researchers realized that time crystals might exist not in equilibrium systems, but in systems driven out of equilibrium by external forces. Instead of trying to create perpetual motion in an isolated system, they could create periodic motion in systems that were periodically driven, like quantum systems being pulsed with laser light at regular intervals. In these driven systems, something remarkable could happen. The system might respond to the external driving, not by oscillating at the same frequency as the drive, but at half that frequency, or some other fraction. It would be like pushing a swing once every second and having it swing back and forth once every 2 seconds, maintaining this unusual rhythm indefinitely. This spontaneous period doubling would represent a genuine breaking of time translation symmetry, creating the temporal equivalent of a crystal lattice. The quantum systems that could exhibit this behavior needed to be carefully engineered. They required just the right combination of interactions, disorder, and driving to maintain their temporal patterns without falling into thermal equilibrium. The systems needed to be what physicists call many-body localized, meaning that the quantum particles within them couldn't efficiently share energy and thermalize the way they normally would. Many-body localization is itself a fascinating phenomenon that occurs in certain disordered quantum systems. When particles are subjected to random potentials and interact with each other in specific ways, they can become trapped in their initial configurations, unable to explore the full range of possible states. This localization prevents the system from reaching thermal equilibrium, preserving quantum coherence and enabling exotic phases of matter to exist indefinitely. In such localized systems, time crystals could emerge as stable phases of matter that persist without any energy input beyond the periodic driving. The system would settle into a pattern where it oscillates with a period longer than the driving period, maintaining this rhythm through the complex interplay of quantum mechanics disorder and many-body interactions. The theoretical foundation was elegant, but proving that time crystals actually existed required experimental verification. The first successful demonstrations came in 2016 and 2017, when 2 independent research groups managed to create and observe time crystal behavior in carefully controlled quantum systems. These experiments represented a triumph of both theoretical understanding and experimental precision. One approach used a chain of trapped atomic ions, individual atoms held in place by electromagnetic fields and manipulated with laser pulses. By carefully tuning the interactions between the ions and applying periodic driving pulses, the researchers could coax the system into a time crystalline phase where it oscillated at half the driving frequency. The system would respond to every other driving pulse, creating a temporal pattern that persisted for hundreds of cycles. Another approach used nitrogen vacancy centers in diamond, quantum defects that act like tiny magnets embedded in the crystal lattice. These systems could be driven with microwave pulses, while their quantum states were monitored with extraordinary precision. Under the right conditions, they too exhibited the signature period doubling that characterizes discrete time crystals. These experimental successes confirmed that time crystals were not merely theoretical curiosities, but real physical phenomena that could be observed and studied in the laboratory. The systems were small and delicate, requiring careful isolation from environmental disturbances, but they demonstrated, beyond doubt, that matter could organize itself in time just as it organizes itself in space. The implications of these discoveries extend far beyond the immediate physics involved. Time crystals represent a new phase of matter, one that exists out of equilibrium and maintains quantum coherence over extended periods. They offer insights into the fundamental nature of time and symmetry breaking, and they might eventually find applications in quantum computing and other advanced technologies. But perhaps most intriguingly, time crystals force us to reconsider our understanding of time itself. They suggest that temporal order can emerge spontaneously from quantum systems, creating patterns in time that mirror the spatial patterns we see in ordinary crystals. This raises profound questions about the relationship between time and matter, and whether time might have structure and texture that we've barely begun to explore. As we continue our journey through this strange landscape where time crystallizes into patterns, we'll discover how these quantum systems challenge our most basic assumptions about the flow of time, and what they might teach us about the deeper rhythms that govern our universe. The existence of time crystals opened a window into something far stranger than most physicists had anticipated. These quantum systems didn't just challenge our understanding of crystals or even of matter itself. They whispered hints about the fundamental nature of time, suggesting that our most basic temporal assumptions might be incomplete. To appreciate just how revolutionary this discovery was, we need to understand what physicists mean when they talk about broken symmetry. In the very breaking everyday world, symmetry is everywhere, though we rarely notice it. When you drop a pencil, it falls in one particular direction, rather than hovering in perfect balance. When water freezes into ice, the H2O molecules choose specific orientations rather than maintaining their liquid randomness. Nature, it seems, has a preference for picking sides. Time translation symmetry is the idea that the laws of physics remain the same whether you perform an experiment today or tomorrow. Time, from this perspective, is uniform and featureless. There's nothing special about any particular moment. Yet time crystals seem to violate this principle, creating systems that spontaneously develop preferred temporal rhythms without any external clock to guide them. Imagine walking through a forest where every tree suddenly started swaying in perfect synchronization, not because of wind or any external force, but simply because they had somehow agreed upon a collective rhythm. This is analogous to what happens in a time crystal, where quantum particles organize their behavior in time without any temporal conductor orchestrating their dance. The quantum systems that exhibit time crystalline behavior exist in a delicate balance between order and chaos. They require just enough disorder to prevent thermal equilibrium, but not so much that all structure is lost. It's like tuning a radio to find that perfect frequency where the signal comes through clearly. Except here, we're tuning the quantum interactions to find the precise conditions where temporal order emerges. Many-body localization plays a crucial role in maintaining this balance. In ordinary materials, energy spreads rapidly through the system as particles collide and interact, eventually reaching a state of thermal equilibrium where all interesting quantum effects are washed out. But in localized systems, this energy spreading is dramatically slowed or even stopped entirely. Picture a crowded party where everyone is trying to move around the room. In a normal situation, people would gradually spread out, mixing and finding comfortable spots where the crowd density becomes uniform. But imagine if each person became somehow stuck in their immediate vicinity, unable to venture far from their starting position. The party would maintain its initial structure indefinitely, with clusters of people remaining isolated from one another. This is essentially what happens in many-body localized systems. Quantum particles become trapped by disorder, unable to efficiently exchange energy with their neighbors. This localization preserves the quantum coherence necessary for time crystal behavior, preventing the system from thermalizing and losing its temporal structure. The driving force in these systems serves a role similar to a metronome, but with a twist. Unlike a mechanical metronome that simply keeps time, the periodic driving in time crystals actively maintains the system's non-equilibrium state. The system doesn't simply follow the driving rhythm. Instead, it develops its own internal tempo that bears a specific mathematical relationship to the external pulse. This phenomenon, known as period doubling, is reminiscent of certain non-linear dynamical systems where complex behaviors emerge from simple driving forces. But in quantum time crystals, the period doubling occurs at the level of quantum states rather than classical trajectories, making it a fundamentally different and more exotic phenomenon. The experimental realization of time crystals required extraordinary precision and control. The trapped ion experiments, for instance, used individual atoms cooled to temperatures just millionths of a degree above absolute zero. At these extreme conditions, quantum effects dominate over thermal motion, allowing researchers to manipulate the quantum states with laser pulses lasting mere microseconds. Each in these ion experiments acts like a tiny quantum compass needle, with its spin pointing either up or down. The researchers could flip these spins using carefully timed laser pulses, creating quantum superpositions where each ion exists in both spin states simultaneously. The interactions between neighboring ions couple their quantum states together, creating a many-body quantum system with rich emergent behavior. When driven with periodic pulses, these ion chains would sometimes settle into a rhythm where their collective spin pattern oscillated with twice the period of the driving force. The system would remember its previous state, responding to every other pulse while ignoring the ones in between. This quantum memory persisted for hundreds of driving cycles, demonstrating the robust nature of the time crystalline phase. The nitrogen vacancy experiments took a different approach, using quantum defects embedded in diamond crystals. These defects act like atomic scale magnets that can be individually addressed and controlled using microwave radiation. Unlike the ion trap systems, which required complex laser cooling and trapping apparatus, the diamond systems operated at room temperature, making them potentially more practical for applications. In both experimental platforms, the key signature of time crystal behavior was the emergence of oscillations at frequencies different from the driving frequency. This wasn't simply a resonance effect, where the system vibrates in response to external forcing. Instead, it represented a genuine spontaneous breaking of time translation symmetry, where the system chose its own temporal rhythm. The robustness of this behavior surprised many researchers. Time crystals proved to be remarkably stable against perturbations and imperfections in the experimental setup. Even when the driving pulses weren't perfectly periodic, or when there was noise in the system, the time crystalline phase persisted. This stability suggested that time crystals represent a new phase of matter with its own characteristic properties and phase transitions. Beyond their fundamental scientific interest, time crystals have sparked discussions about potential applications. Their ability to maintain quantum coherence over extended periods makes them interesting candidates for quantum memory devices. Their sensitivity to external perturbations could make them useful as quantum sensors. Their non-equilibrium nature might provide insights into biological systems that operate far from thermal equilibrium. But perhaps the most profound implications of time crystals lie in what they reveal about the nature of time itself. These systems suggest that time can have texture and structure, that it can be organized and patterned in ways we hadn't previously imagined. They hint at deeper connections between quantum mechanics and temporality that we're only beginning to explore. The discovery of time crystals also raises intriguing questions about the arrow of time. In classical physics, the distinction between past and future emerges from the second law of thermodynamics, which dictates that entropy always increases. But time crystals exist in non-equilibrium states where traditional thermodynamic reasoning breaks down. Do these systems experience time differently? Do they provide clues about how temporal asymmetry emerges in quantum systems? Some theorists have speculated about connections between time crystals and more exotic possibilities, such as closed time-like curves or temporal paradoxes. While such connections remain highly speculative, they illustrate how time crystals challenge our conventional understanding of causality and temporal flow. These quantum systems seem to dance to rhythms that exist outside our normal experience of time. The mathematics underlying time crystals reveals deep connections to other areas of physics. The same mathematical structures that describe phase transitions in space also apply to temporal phase transitions. The concept of spontaneous symmetry breaking, fundamental to particle physics and condensed matter theory, takes on new meaning when applied to time rather than space. Research into time crystals has also illuminated connections to quantum many-body scars, another exotic quantum phenomenon where certain special quantum states resist thermalization. These scar states create long-lived oscillations in quantum systems that would normally rapidly reach equilibrium. The relationship between time crystals and quantum scars suggests that non-equilibrium quantum phenomena might be more common and varied than previously thought. As experimental techniques improve and theoretical understanding deepens, researchers are discovering new varieties of time crystals with different properties and behaviors. Some systems exhibit period doubling, others show more complex temporal patterns, and still others demonstrate continuous time translation symmetry, breaking rather than discrete oscillations. The field has expanded beyond the original ion trap and diamond experiments to include superconducting circuits, ultra-cold atomic gases, and even room-temperature molecular systems. Each platform offers unique advantages and insights, contributing to our growing understanding of how quantum matter can organize itself in time. These diverse experimental realizations have revealed that time crystalline behavior is not confined to a single type of quantum system, but represents a more general phenomenon that can emerge whenever the right conditions are met. The universality of time crystal behavior suggests that temporal organization might be a fundamental feature of quantum many-body systems, waiting to be discovered in natural systems as well as artificial ones. As we peer deeper into the quantum realm, where time crystals dance their eternal rhythms, we find ourselves confronting questions that stretch far beyond physics into philosophy and consciousness. Does it mean for itself? What time to have structure? How does temporal order emerge from quantum chaos? And what might teach us about the deep, these discoveries, this nature of reality? The pursuit of time crystals has led physicists into territories where intuition fails and mathematics becomes poetry. As researchers probe deeper into these temporal structures, they've discovered that time crystals are not merely curiosities, but windows into a more fundamental understanding of how reality organizes itself when freed from the constraints of equilibrium. Consider how profound this revelation truly is. For centuries, we've understood that all physical systems naturally evolve toward states of maximum entropy, toward thermal equilibrium, where all interesting dynamics cease. It's the reason why hot coffee cools to room temperature, why perfume disperses through air, why the universe itself seems destined for a state of maximum disorder. Yet time crystals exist in defiance of this universal tendency, maintaining their coherent oscillations indefinitely without ever settling into the bland uniformity of thermal equilibrium. This resistance to thermalization doesn't violate any fundamental laws of physics, but it does reveal how narrow our previous understanding had been. We had assumed that interesting quantum phenomena could only persist at extremely low temperatures, or for very brief moments before decoherence destroyed all quantum coherence. Time crystals shatter this assumption, showing us quantum systems that maintain their exotic properties even when subjected to noise, imperfections, and the relentless tendency toward disorder. The mechanisms that protect time crystals from thermalization are as elegant as they are subtle. The interplay between disorder, interactions, and driving creates a kind of quantum fortress where temporal order can flourish. The disorder prevents the system from finding a simple path to equilibrium, while the interactions between particles create correlations that resist the spread of energy. The periodic driving maintains the system in a state far from equilibrium, where conventional thermodynamic rules no longer apply. But perhaps the most remarkable aspect of time crystals is how they seem to create their own temporal reference frame. In ordinary matter, time appears uniform and featureless from the perspective of the constituent particles. Electrons and atoms experience time as a smooth flow, unmarked by any intrinsic structure. Time crystals, however, establish their own internal chronometer, beating to rhythms that emerge spontaneously from their quantum interactions. This internal timekeeping raises fascinating questions about the relationship between subjective and objective time. From our external perspective, we observe the time crystal oscillating with a period different from our driving frequency. But what would time of the quantum system itself? Would it look like, from the perspective experience, its own oscillations as natural and our external driving as the anomaly? These questions venture into territory that borders on consciousness and perception, reminding us that time may not be the universal, objective quantity we usually assume it to be. Different physical systems might experience temporal flow in fundamentally different ways, each carrying their own internal clocks that tick according to their unique quantum dynamics. The study of time crystals has also revealed unexpected connections to some of the deepest problems in theoretical physics. The same mathematical frameworks that describe temporal symmetry breaking in these quantum systems also appear in discussions of the cosmological arrow of time and the emergence of classical space-time from quantum gravity. Some theorists speculate that time crystals might provide insights into how time itself emerges as a macroscopic concept from more fundamental quantum processes. In the realm of quantum field theory, time crystals challenge our understanding of vacuum states and ground state properties. The traditional picture of the vacuum as an empty, featureless state begins to blur when we consider systems that can spontaneously develop temporal structure, even in their lowest energy configurations. These discoveries hint at a richer, more dynamic picture of quantum vacuum states that might have implications for our understanding of particle physics and cosmology. The experimental techniques developed to study time crystals have pushed the boundaries of quantum control and measurement. Researchers have learned to manipulate individual quantum states with unprecedented precision, to maintain quantum coherence for extraordinarily long periods, and to detect subtle signatures of temporal order in noisy quantum systems. These advances have applications far beyond time crystals themselves, contributing to the development of quantum computers, quantum sensors, and other quantum technologies. Some of the most exciting developments have come from exploring time crystals in different physical platforms. Superconducting quantum circuits have enabled researchers to study time crystalline behavior in artificial atoms coupled to microwave resonators. These systems offer exquisite control over parameters and the ability to engineer interactions that would be impossible in natural materials. Ultra-cold atomic gases have provided another fertile testing ground for time crystal physics. In these systems, researchers can create synthetic gauge fields and exotic interactions using laser light, essentially building artificial universes with custom-designed physical laws. The ability to tune interactions in real time has led to observations of dynamical phase transitions, where systems suddenly switch between different temporal patterns. Even biological systems have entered the conversation, as researchers explore whether living organisms might exhibit time crystalline behavior. The complex biochemical networks that regulate cellular processes operate far from thermal equilibrium and display intricate temporal patterns. Some scientists speculate that certins might represent biological naturally occurring time crystals, evolved to maintain coherent temporal organization in the noisy environment of living cells. The philosophical implications of time crystals extend beyond their immediate physical properties. They suggest that temporal order might be as fundamental as spatial order in organizing matter and energy. Just as crystals represent the spontaneous organization of matter in space, time crystals might represent the spontaneous organization of processes in time. This perspective opens new ways of thinking about complex systems more generally. Perhaps many of the patterns we observe in nature, from the rhythms of ecosystems to the cycles of economic activity, represent forms of temporal crystallization, where order emerges spontaneously from apparently random processes. The mathematics of time crystals might provide tools for understanding how temporal patterns arise and persist in systems far from equilibrium. The discovery that matter can organize itself in time also raises questions about the fundamental nature of physical law. Are the laws of physics themselves temporal patterns that have crystallized out of some more fundamental quantum substrate? Could the constants of nature, which appear fixed to us, actually be oscillating on timescales too long for us to detect? These speculations push us toward the edges of scientific knowledge, where physics begins to merge with metaphysics. Recent theoretical work has explored the possibility of higher dimensional time crystals, systems that break multiple temporal symmetries simultaneously. These exotic phases of matter would exhibit complex temporal patterns with multiple interwoven periodicities, creating temporal structures as intricate as the spatial lattices found in conventional crystals. While such systems remain largely theoretical, they illustrate how rich the landscape of temporal organization might be. The search for continuous time crystals, systems that break time translation symmetry in a smooth rather than discrete manner, has led to investigations of quantum systems with unusual symmetry properties. These would be systems that oscillate continuously rather than jumping between discrete states, potentially offering even more exotic forms of temporal organization. As the field has matured, researchers have begun to classify different types of time crystalline behavior and to understand the phase transitions between them. Just as conventional crystals can melt or undergo structural phase transitions, time crystals can transition between different temporal patterns or lose their time crystalline order altogether. These temporal phase transitions represent a new class of quantum phenomena with their own universal properties and scaling laws. The stability of time crystals against various types of perturbations has proven to be one of their most remarkable features. Unlike many quantum phenomena that are extremely fragile and easily destroyed by environmental noise, time crystals can maintain their temporal patterns even in the presence of significant disorder and decoherence. This robustness suggests that temporal order might be more fundamental and persistent than previously imagined. Some researchers have begun to explore the possibility of using time crystals as a new type of quantum memory, where information is stored not in the spatial configuration of quantum states, but in their temporal patterns. Such temporal quantum memories might offer advantages in certain types of quantum computation or quantum communication protocols. The study of time crystals has also shed light on the relationship between classical and quantum descriptions of time. While classical physics treats time as a smooth, continuous parameter, quantum mechanics introduces fundamental uncertainties and discreteness into temporal measurements. Time crystals exist at the boundary between these two descriptions, exhibiting classical-like periodic behavior that emerges from purely quantum processes. As we continue to explore these strange temporal territories, we find ourselves confronting questions that extend far beyond the laboratory. What does it mean for time to have texture and pattern? How does temporal organization emerge from quantum chaos? And what might these discoveries reveal about the deepest levels of reality, where time, space, and matter dance together in ways we're only beginning to understand? The quantum landscape where time crystals exist has revealed itself to be far richer and more varied than anyone initially imagined, as they've discovered that the researchers have delved deeper into these temporal structures. Original discrete time crystals were merely the first notes in a much grander symphony of temporal organization. New varieties have emerged from laboratory observations, each with their own unique signatures and behaviors, painting a picture of quantum matter that can organize itself in time with remarkable creativity. One of the most intriguing developments has been the discovery of prethermal time crystals, systems that exhibit time crystalline behavior for extraordinarily long periods before eventually succumbing to thermalization. These systems exist in a kind of temporal limbo, neither fully equilibrated nor permanently organized, maintaining their oscillatory patterns for times that can exceed the age of the universe before finally relaxing into thermal equilibrium. The mathematics governing these pre-thermal phases reveals a delicate dance between competing timescales. On one hand, there's the natural relaxation time of the quantum system, the period over which it would normally thermalize and lose all memory of its initial state. On the other hand, there's the much longer timescale over which the driving and interactions conspire to maintain temporal order. When these timescales are sufficiently separated, the system can remain locked in its time crystalline phase for periods that are, for all practical purposes, infinite. This discovery has profound implications for our understanding of quantum thermodynamics. It suggests that the journey to thermal equilibrium, which we often think of as inevitable and relatively rapid, can be dramatically slowed or even temporarily halted under the right conditions. The universe, it seems, has found ways to resist its own tendency toward maximum entropy, at least for quantum systems carefully balanced on the edge between order and chaos. Researchers have also uncovered time crystals that exhibit more complex temporal patterns than simple period doubling. Some systems oscillate with periods that are 3, 4, or even higher multiples of the driving frequency. Others display quasi-periodic behavior, where the temporal pattern never exactly repeats, but maintains a complex, almost musical structure over time. These discoveries have expanded our vocabulary for describing temporal order, requiring new mathematical frameworks to capture their subtle rhythms. The exploration of time crystals in different spatial dimensions has yielded another layer of complexity. While the original experiments focused on one-dimensional chains of particles, researchers have successfully created time crystals in 2- and 3-dimensional systems. These higher-dimensional time crystals can exhibit spatial patterns that evolve in time, creating dynamic structures where both space and time are organized into crystalline order. Imagine watching a 2-dimensional array of quantum particles where waves of temporal organization sweep across the surface in regular patterns. These are time crystals that exist not just in time, but in space-time, creating 4-dimensional structures of order that challenge our ability to visualize, but offer new insights into the fundamental nature of quantum organization. The study of quantum coherence in time crystals has revealed mechanisms that seem to violate our intuitive understanding of how quantum systems should behave. In ordinary quantum systems, coherence is fragile, easily destroyed by interactions with the environment or by the system's own internal dynamics. Time crystals, however, seem to thrive on these very interactions, using them to maintain and even strengthen their temporal coherence. This phenomenon, sometimes called coherence protection, emerges from the same many-body localization that prevents thermalization. The quantum entanglement between particles in the system creates a web of correlations that resists decoherence, allowing quantum superposition states to persist far longer than would normally be possible. It's as though the quantum system has learned to use its own complexity as a shield against the forces that would normally destroy quantum coherence. Recent theoretical work has begun to explore the possibility of time crystals existing in open quantum systems, environments where the system continuously exchanges energy and information with its surroundings. These would represent an even more exotic form of temporal organization, where the system maintains its oscillatory patterns, not despite environmental interaction, but because of it. The mathematics of open quantum systems introduces new complexities, requiring researchers to account for the continuous flow of energy and information across system boundaries. Yet preliminary studies suggest that under certain conditions, this exchange can actually stabilize time crystalline phases, creating temporal patterns that are sustained by their interaction with the environment rather than isolated from it. Such open time crystals would blur the boundary between living and non-living systems, exhibiting the kind of dynamic stability that characterizes biological processes. They might provide insights into how living organisms maintain their complex temporal patterns while continuously exchanging matter and energy with their surroundings. The connection between time crystals and biological rhythms has become an area of intense interest. Many biological systems exhibit remarkably stable periodic behaviors, from the circadian rhythms that govern sleep and wakefulness, to the oscillatory patterns of neural activity in the brain. While these biological rhythms operate through different physical mechanisms than quantum time crystals, they share the fundamental property of maintaining temporal order in noisy, non-equilibrium environments. Some researchers have speculated about whether quantum effects in biological systems might give rise to genuine biological time crystals. The warm, wet environment of living cells would seem hostile to quantum coherence, but recent discoveries of quantum effects in photosynthesis and possibly in neural microtubules suggest that biology may have found ways to exploit quantum phenomena even under seemingly adverse conditions. The possibility of time crystals existing in biological systems opens tantalizing questions about the role of temporal organization in life itself. Could the precise timing of biochemical processes represent a form of temporal crystallization? Might the remarkable stability of biological rhythms emerge from quantum mechanical principles rather than purely classical feedback mechanisms? These questions push the boundaries of both physics and biology, suggesting new interdisciplinary approaches to understanding life as a temporal phenomenon. The tools developed to study quantum time crystals might eventually be applied to biological systems, revealing new layers of organization in the complex dance of molecules that sustains living organisms. The technological implications of time crystals continue to unfold as researchers develop new applications for these exotic quantum systems. Beyond their potential use in quantum computing and sensing, time crystals might enable entirely new classes of devices that exploit temporal rather than spatial organization. Quantum clocks based on time crystal oscillations could offer unprecedented precision in timekeeping, potentially surpassing even atomic clocks in their stability and accuracy. Such devices would be immune to many of the environmental perturbations that affect conventional timepieces, maintaining their temporal reference even in harsh conditions. Time crystals might also enable new forms of quantum communication, where information is encoded not in the spatial arrangement of quantum bits, but in their temporal patterns. This temporal encoding could offer advantages in certain communication protocols, providing additional dimensions for information storage and transmission. The energy landscape of time crystals has revealed another surprising property. These systems can sometimes exhibit negative effective temperatures, where higher energy states are more probable than lower energy states. This temperature inversion creates unusual thermodynamic properties that could be exploited in quantum heat engines or refrigeration systems. Such quantum thermal machines would operate according to principles that seem to violate our everyday understanding of heat flow and energy conversion. They represent a new frontier in quantum thermodynamics, where the strange properties of time crystals might enable energy conversion processes that are impossible systems. The in-classical study of time crystals has also illuminated connections to other exotic phases of quantum matter. Researchers have discovered relationships between time crystalline behavior and topological phases, quantum spin liquids, and many-body localization. These connections suggest that temporal organization might be a more universal feature of quantum systems than previously recognized. The classification of different time crystal phases has become a rich area of theoretical research, with physicists developing new mathematical tools to describe and categorize the various forms of temporal order. Just as conventional crystals are classified according to their spatial symmetries, time crystals are being organized according to their temporal symmetries and the nature of their oscillatory patterns. This classification scheme has revealed that the space of possible time crystal phases is vast and largely unexplored. Many theoretical possibilities remain to be discovered experimentally, suggesting that we have only glimpsed the beginning of what promises to be a rich new field of quantum matter research. As experimental techniques continue to improve, researchers are pushing toward ever more ambitious demonstrations of time crystalline behavior. Plans are underway for space-based experiments that could observe time crystals free from terrestrial vibrations and magnetic field fluctuations. Such experiments might reveal new aspects of temporal organization that are hidden by the noise and imperfections of Earth-based laboratories. The quest to understand time crystals has also driven advances in quantum simulation, where researchers use one quantum system to model another. These quantum simulators allow scientists to explore exotic phases of matter that might be impossible to create directly, opening windows into theoretical landscapes that exist only in the equations of quantum field theory. Through quantum simulation, researchers have begun to explore time crystals in curved spacetime, investigating how temporal organization might be affected by gravitational fields or accelerated motion. These studies bridge quantum mechanics and general relativity, suggesting new connections between temporal symmetry breaking and the fundamental structure of spacetime itself. The philosophical implications of time crystals continue to deepen as our understanding of these systems evolves. They challenge our most basic assumptions about the nature of time, suggesting that temporal flow might be far more structured and complex than our everyday experience suggests. In a universe where matter can organize itself in time as readily as in space, the boundary between temporal and spatial becomes increasingly blurred. These discoveries invite us to reconsider our relationship with time itself, to see it not as an empty stage upon which events unfold, but as an active participant in the dance of existence. Time crystals whisper to us about deeper rhythms that pulse through the quantum fabric of reality, patterns that exist beyond our direct perception, but shape the very foundations of the physical world. As we continue to explore these strange temporal territories, we find ourselves standing at the threshold of a new understanding of time, matter, and the subtle ways they interweave to create the rich tapestry of existence. The story of time crystals is still being written, each new discovery adding another verse to the cosmic song that flows through the quantum heart of reality. As we drift deeper into the strange realm where time itself can crystallize, we encounter phenomena that seem to dissolve the very foundations of temporal experience. These quantum systems don't merely challenge our understanding of matter or energy, they invite us to reconsider the nature of causality itself, whispering secrets about how cause and effect might flow through crystallized time. In ordinary experience, causality follows a simple pattern. Events in the past influence the present, which in turn shapes the future. Time serves as the organizing principle that keeps cause separated from effect, ensuring that events unfold in logical sequence. But in time crystals, this familiar ordering begins to blur in ways that are both subtle and profound. Consider what happens when a quantum system oscillates at half the frequency of its driving force. From one perspective, each driving pulse causes the system to evolve, but the system responds by creating its own internal rhythm that spans multiple driving cycles. The question becomes, which is the cause and which is the effect? Is the system responding to individual pulses, or is it following some deeper pattern that transcends the immediate driving? This temporal ambiguity emerges from the quantum nature of time crystalline states. Unlike classical systems, where cause and effect follow clear trajectories, quantum systems exist in superpositions of multiple possible histories. A time crystal maintains quantum coherence across multiple time periods, creating correlations that span past, present, and future in ways that challenge our linear understanding of temporal flow. The mathematics describing these correlations reveals something remarkable. Time crystals exhibit what physicists call non-local correlations in time, similar to the spatial entanglement that Einstein famously called spooky action at a distance. But here, the spookiness occurs across temporal rather than spatial separation. The quantum state at one moment can be mysteriously correlated with states at distant future moments, creating temporal entanglement that defies our intuitive understanding of how time should work. These temporal correlations don't violate causality in any measurable way, but they do reveal how limited our classical picture of cause and effect really is. In the quantum realm, the sharp distinction between past and future becomes fuzzy, replaced by a more fluid understanding where different moments in time can be quantum mechanically entangled with one another. The implications extend beyond individual time crystals to the broader question of how temporal structure emerges from quantum processes. Some theorists have begun to explore whether time itself might be an emergent property, arising from more fundamental quantum interactions, rather than existing as an absolute backdrop against which events unfold. Time crystals provide concrete examples of how temporal patterns can spontaneously emerge from quantum systems, suggesting that time's apparent universality might be more complex than we've assumed. Recent experiments have pushed these ideas into even stranger territory by creating time crystals that exhibit multiple temporal scales simultaneously. These systems oscillate with several different periods at once, creating complex temporal patterns that weave together like musical harmonies. The result is a kind of temporal symphony where different aspects of the quantum system dance to different rhythmic patterns, all maintained coherently within the same physical system. Imagine a quantum orchestra where different sections keep time according to different metronomes, yet somehow maintain perfect harmony. This is analogous to what researchers observe in these multi-period time crystals, where quantum coherence allows seemingly incompatible temporal rhythms to coexist within a single system. The stability of these complex temporal patterns raises fascinating questions about information storage and processing in quantum systems. If a system can maintain multiple coherent oscillations simultaneously, it might be possible to encode information in the relationships between these different temporal modes. This could lead to new forms of quantum computing, where calculations are performed not through spatial manipulation of quantum bits, but through the temporal evolution of crystallized time patterns. Such temporal quantum computers would operate according to principles that seem almost mystical from our classical perspective. Instead of gates that flip quantum bits in space, they would use temporal operations that manipulate the phase relationships between different oscillatory modes. The computation would unfold not through a sequence of logical operations, but through the natural evolution of temporal patterns encoded in the quantum system. The energy flow in these systems reveals yet another layer of temporal rangeness. Unlike classical systems where energy dissipation marks the arrow of time, time crystals can maintain their patterns while continuously cycling energy through different modes. The system neither gains nor loses energy on average, but the energy itself becomes temporally structured, flowing in patterns that mirror the crystalline organization of the quantum states. This temporal structuring of energy creates what some researchers call temporal textures, where the flow of energy through the system exhibits the same kind of organization that we see in the spatial textures of conventional materials. Just as a fabric has a characteristic weave that determines its properties, time crystals have characteristic temporal weaves that determine how energy and information flow through them. The discovery of temporal textures has opened new avenues for understanding how complex systems maintain their organization over time. Many natural phenomena, from weather patterns to ecosystem dynamics, exhibit temporal structures that persist despite constant energy flow. The principles governing time crystals might provide insights into how these natural systems maintain their temporal coherence. Biological systems, in particular, exhibit remarkable temporal organization that spans multiple scales, from the rapid oscillations of neural activity to the slow rhythms of seasonal cycles. Some researchers have begun to investigate whether biological temporal patterns might emerge from quantum processes similar to those found in time crystals, though the warm, noisy environment of living systems presents significant challenges to maintaining quantum coherence. The search for biological time crystals has led to investigations of quantum effects in neural networks, where some theorists propose that consciousness itself might emerge from temporal quantum coherence in brain tissue. While such ideas remain highly speculative, they illustrate how time crystals have expanded our thinking about the role of temporal organization in complex systems. The relationship between time crystals and consciousness touches on some of the deepest questions in science and philosophy. If time can be structured and organized at the quantum level, what does this mean for our subjective experience of temporal flow? Could the sense of duration and sequence that characterizes consciousness emerge from quantum temporal processes occurring in neural tissue? These questions venture into territory where physics meets neuroscience and philosophy, where the objective study of temporal phenomena encounters the subjective experience of time's passage. Time crystals don't provide direct answers to these profound questions, but they do suggest that time is far more malleable and structured than our everyday experience suggests. The applications of time crystal technological research continue to expand as scientists develop new ways to harness temporal organization for practical purposes. Beyond quantum computing and precision timekeeping, researchers are exploring applications in quantum sensing, where the temporal stability of time crystals could enable detection of extremely subtle environmental changes. Time crystal sensors would operate by detecting tiny perturbations in their temporal patterns, potentially offering sensitivity to magnetic fields, gravitational waves, or other physical phenomena that leave barely detectable signatures. The long-term stability of these systems could allow for sensing applications that require sustained observation over extended periods. The development of time crystal technology has also driven advances in quantum control, where researchers have learned to manipulate quantum systems with unprecedented precision. These techniques have applications far beyond time crystals themselves, contributing to progress in quantum computing, quantum communication, and fundamental physics research. Some of the most exciting prospects involve using time crystals to explore the intersection of quantum mechanics and general relativity. Researchers have proposed experiments where time crystals are subjected to strong gravitational fields or accelerated motion, potentially revealing new connections between quantum temporal organization and the curvature of space-time. Such experiments could provide insights into quantum gravity, the long-sought theory that would unify quantum mechanics with Einstein's general relativity. Time crystals, with their unique relationship to temporal symmetry, might serve as probes for understanding how quantum phenomena behave in curved spacetime. The mathematical framework developed to understand time crystals has also found applications in other areas of theoretical physics. The same techniques used to analyze temporal symmetry breaking have been applied to problems in particle physics, cosmology, and string theory, revealing unexpected connections between seemingly disparate areas of research. These mathematical connections suggest that temporal organization might be a more fundamental feature of physical law than previously recognized. The principles that govern time crystal formation could be manifestations of deeper symmetries that operate throughout the universe, from the smallest quantum scales to the largest cosmological structures. As research continues, New varieties of time crystals emerge regularly from the laboratories around the world. Each new discovery adds another note to the growing symphony of temporal phenomena, revealing the rich landscape of possibilities that exists when quantum matter learns to organize itself in time. The field has evolved from a theoreticalizing area of experimental research curiosity to a THR, with applications ranging from fundamental physics to quantum technology. Yet, for all the progress, the deepest questions about time crystals remain tantalizingly open, inviting further exploration into the strange quantum realm, where time itself dances to rhythms we're only beginning to understand. These crystallized moments in time continue to whisper their secrets, each oscillation a gentle reminder that the universe holds patterns and structures far more subtle and beautiful than our everyday experience suggests. In their quiet persistence, time crystals offer us a glimpse into the deeper rhythms that pulse through the quantum heart of reality, inviting us to reconsider our most basic assumptions about the nature of time and existence itself. And so we find ourselves at the end of our gentle journey through the crystallized corridors of time, where quantum matter has learned to dance to rhythms that exist beyond our ordinary experience. We've witnessed how these exotic systems challenge our most fundamental assumptions about temporal flow, revealing a universe where time itself can organize into patterns as intricate and beautiful as any crystal found in nature. From Frank Wilczek's initial theoretical whisper to the laboratory confirmations that followed, time crystals have opened windows into realms where the familiar rules of thermodynamics bend and flex, where quantum systems maintain their coherent oscillations indefinitely, and where the very notion of temporal symmetry takes on new meaning. These discoveries remind us that even in a cosmos we think we understand, there are always deeper mysteries waiting to be unveiled. Perhaps most remarkably, time crystals invite us to reconsider our relationship with time itself. They suggest that temporal flow might be far richer and more structured than our everyday experience reveals, filled with textures and patterns that pulse through the quantum fabric of reality. In their quiet persistence, these systems whisper to us about the profound interconnectedness of time, matter, and consciousness. As you settle back into the familiar flow of ordinary time tonight, perhaps you'll carry with you a sense of wonder about the deeper rhythms that surround us, the temporal crystalline structures that might be oscillating just beyond our perception, keeping time to cosmic melodies we're only beginning to hear. Sweet dreams, fellow travelers of the whispering galaxy, until we meet again to explore the next gentle mystery that awaits us in the infinite dance of existence.